All right, guys, it's time to get serious with summation notation. So summation notation is just a way of representing a whole bunch of addition without actually writing out all of the addition. Rather, we're going to leave that for somebody else, mainly you guys, to write out all the addition. But summation notation uses sigma, which is this big E thing, and then sequence notation. So in the sigma, you have a formula for the sequence, an explicit formula, saying if you plug in this index, you will get out this value. And then on the sigma, at the bottom, you will have an initial index and sometimes a variable, so that should match the variable in your formula. And at the very top, your terminal index, or your final index, where you would stop. And we would read this as the sum of terms a sub I through a sub t. And that's all it means. Just add the terms a sub I to a sub t. So as an example here, we have the sum from a sub 3 to a sub 6 of the sequence 3x plus 2. So I need to add together a sub 3, a sub 4, a sub 5, and a sub 6. So I need to find those values, and that's where the sequence formula comes in. I know if I have the explicit formula, all I have to do is plug in the index, and it will tell me the values. That's exactly what I'm going to do. So for 3 times 3 is 9, plus 2 is 11. So the third term in this sequence was 11. And then I just kind of go up from there. 4, 5, 6, just like we did there. 3 times 4 is 12, plus 2 is 14. 3 times 5 is 15, plus 2 is 17. And 3 times 6, which would be my terminal index, 3 times 6 is 18, plus 2 is 20. This is the series. And if we add those all up, we get a partial sum. 11 plus 14 plus 17 plus 20 is 62. It's a partial sum because sequences go on forever, and so we've only got a part of the sequence added together. Here's our series, 11, 14, 17, 20, with addition or subtraction between them. That's all summation notation is. Okay. So let's look at a few examples of that. Here we go. This is from the summation notation intro on Khan Academy. It wants us to add from 0 to 2 of 2k plus 2. So we need to find a sub 0, a sub 1, and a sub 2. And we get those just by plugging them into the sequence formula they gave us. 2 times 0 is 0, plus 2 is 2. So it'd be 2 times 0 plus 2. 2 times 1 is 2, plus 2 is 4. And we already really have this pattern. It's 2, 4, 6. But just to give you an idea of how we're getting there. And then 2 times 2 plus 2 gives me 6. And then I just add those together. So 2 plus 4 is 6, plus 6 is 12. So the sum of the terms a sub 0 to a sub 2 given by this sequence is 12. Same idea. This is just a sub 0 and a sub 1. And again, if we plug those in, 4 minus 0 is 4. 4 minus 1 is 3. That's all the terms from 0 to 1. So 4 plus 3 is 7. In this case, we want the sum from 1 to 3, so term 1 to term 3 of n minus 1. So we'd have a sub 1, a sub 2, and then our terminal index would be 3, a sub 3. 1 minus 1 is 0, 2 minus 1 is 1, 3 minus 1 is 2, and my sum is equal to 3. And this one's the same. I'm not going to worry about doing it. It works exactly the same way. So we'll move on. Now, things like this. The sum from 1 to 425 of 9k minus 3,219. On the last examples, we could just write out the terms. There were like 3 or 2 of them. So it's just expanding to the series and then adding them up. That's not really feasible for this one, since going from term 1 to 425 is 425 terms. I don't really want to write those all out. However, this is linear. So if that sequence formula is linear, then it's arithmetic. So we have a formula. It's an arithmetic sequence, so we can use that. So, if our series is arithmetic, which again, we use if the sequence formula is linear, that's how I knew to use this, then the nth partial sum is n over 2, where n is the number of terms, and then in the parentheses, the initial term plus the terminal term, the final term. So let's look here. We have an example. It is 5 to 372 of 2x minus 100. Well, this sequence formula, 2x minus 100, is linear. It's mx plus b. So that tells me I can use the formula. I need to know the number of terms. So I have to know how many terms are there from a sub 5 to a sub 372. That's very easy. It's the top minus the bottom plus 1. So here I'm going to do 372 minus 5 plus 1. Okay. Top minus the bottom, and then plus 1. Then I need to find a sub 5 and a sub 372. I need to find those values. So I just plug in. 2 times 5 is 10. Minus 100, that's negative 90. For a sub 372, I do 2 times 372 minus 100, and we end up with 644. And then it's just a matter of evaluating that. So let's go ahead and take care of this first. 372 minus 5 plus 1 is 368. So we are adding 368 terms together here. Negative 90 plus 644 is 554. So we can do 368 divided by 2 times that. And we end up with 101,936. So we're just going to use that formula on the exercise with arithmetic series, finite arithmetic series, which means they do not go to infinity. We're going to use this formula. So that's what we would do where we left off on Khan Academy. So let's go back there. Now I know that it is arithmetic, it's linear. So going to have over 2, but top minus the bottom plus 1, which you can see if the bottom is 1, this is just going to cancel out and it's going to be the top number. But like on the example, if the bottom index is not 1, then we can use this top minus bottom plus 1 to actually find the number of terms. And we're going to do that for arithmetic and geometric if they don't start at 1. Then I need to find a sub 1's value and a sub 425's value. So a sub 1 is 9 minus 3,219. It's going to be negative 3,210. And then to get our 425th term, we're going to plug in 425 to our sequence formula. So we have 9 times 425 minus 3,219. And we have 606. So then I can just start evaluating this formula. Which would be 425 over 2 times negative 3,210 plus 606 is negative 2,604. And then I just evaluate that. So 425 times a negative 2,604 divided by 2 is negative 553,350. So put that in. Negative 553,350. Okay. And notice that took me a lot less time than if I had tried to write out all 425 terms. Okay. Now, this one did not give me my summation notation. Instead, it gave me the number. But I can see that each time, negative 32, negative 34, negative 36, each time we go from one term to the next, they're just subtracting 2. I don't know which one this is, though. So I have to build my summation notation. Let's start at index 1. Let's do A. I don't know what this last index is, but I can build my formula in that I know A sub n is equal to A sub 1 plus the difference n minus 1 times. So arithmetic sequence formula. And I'm going to simplify this. That's going to be negative 32 minus 2n plus 2. So we get negative 2n minus 30. So now I've got my sequence formula, recognizing that it was a linear pattern or arithmetic, and then using that arithmetic sequence formula there. all I have to do now is figure out my last index value, which I used A, didn't I? So I'm going to make sure my variable matches. It's a very bad habit that I keep switching my variable around. But now I got to figure out this negative 780, but I can just use this. Negative 780 is equal to negative 2n minus 30. And solving this will give me the index of that last term. So I can do it that way. So negative 780 plus 30 divided by negative 2 is 375. Which means that's the 375th term of that series, of that sequence, excuse me. And now I can finally find the sum. S sub n is 375 minus 1 plus 1 over 2. And we actually already knew the first and last term. We know the first term is negative 32. And the last term is negative 780. Run out of room. All right. So then we start evaluating that. Negative 32 plus negative 780 is negative 812. So we have 375 over 2 times negative 812. So times 375 divided by 2. And we have negative 152,250. Let's type that in, negative 152,250. The arithmetic sequence is defined by the formula. Find the sum of the first 880 terms in the sequence. So what they're asking is the sum from 1 to 880. But that's the recursive formula. I don't want the recursive formula. I want the explicit formula. So I'm going to use the negative 53 plus 6 n minus 1 times to get my sequence formula, A sub n. And that's going to be negative 53 minus 6, so negative 59 plus 6n is what's going to go here. So let's do plus. No. We'll go ahead and change the order around to make it easier to work with as well. So we put 6n minus 59. You notice I took the information that I was given and I kind of rewrote it so it matched the question. This is asking for the sum of the first 880 terms in the sequence. Summation notation is going to fit a lot better for that. So I did from 1 to 880 of my sequence formula. And they gave me the recursive formula, which is not going to be great for building 880 terms. So I want the explicit formula, so I went ahead and found that too and simplified it. And now we can find our partial sum. Here, S sub n would be 880 minus 1 plus 1 over 2. First term is going to be, well, we know the first term is negative 53. So 6 times 1 minus 59 is negative 53. The last term is going to be 6 times 880 minus 59. It's 5221, 5,221. Okay. And again, this is the boring part. We just do the addition. So 880 divided by 2 is 440. And then the negative 53 plus 5, 5221. is 5,168. So we multiply those together times 440, and we get 2,273,920. I'm really going in for the big numbers here. 273,920. $2,273,920. And that one's just like the first one, so good. We're going to go ahead now. What if it's not arithmetic? What if instead it's geometric, which means it has a multiplying pattern? It is a geometric sequence. Well, then we can't use the arithmetic formula anymore, but we can use the geometric formula, which is just as good. In fact, it's a little easier because we don't ever have to find the last term in the sequence. We just need to know the initial term and the exponential base, or the rate of growth, when we're talking about exponential, and the number of terms in the sequence. So for instance, this one. If I wanted to find this sum, I need to find a sub 2 times 1 minus 2, and then, just like we did with arithmetic, top minus bottom plus 1. So 10 minus 2 is 8, plus 1 is 9. This would be my formula. A sub 2 would be 3 times 2 to the first power. So we'll write that on. A sub 2 would be 3 times 2 to the 2 minus 1 power, which is just 6. So we could get rid of that and write in 6. Be careful. Exponents come first. Don't do that subtraction and then raise it to the power. It's 2 to the 9th taken away from 1. So we're going to do 2 to the 9th power, which is 512. So I'm going to actually write out that step. So we have 6 times 1 minus 512 over 1 minus 2. So 6, 1 minus 512 times 6 divided by, on the bottom, which just be negative 1, is 3,066. So just like with the arithmetic series, if they give me the summation notation, that's great, I can use that. If not, I'll have to use the information they give me to kind of work through the problem. But it's doable, and it's always going to be back to this formula. So let's go see a few examples of that now. Like this one. Find the sum of the first 35 terms in this geometric series. So that's 1 to 35. And then I need to build the pattern. But I know from the geometric sequences, the pattern is a sub I times r to the n minus 1 power. So 8 is my first term. Now I need to figure out the ratio. What am I multiplying by each time to go from term to term? So I go from 8 to negative 12, from negative 12 to 18. Well, let's just look at the ratio. Negative 12 over 8 is equal to negative 3 halves. 18 over negative 12 is also negative 3 halves. That's my rate. That's what we're multiplying by each time. Negative 3 over 2 to the n minus 1 power. And although that fraction may not be something we look forward to working with, it is something we can work with in our formula. So that's exactly what we're going to do here. Our formula would be 8 times 1 minus negative 3 halves to the 35th power over 1 minus negative 3 halves. And it's one thing at a time. So negative 3 over 2 to the 35th power. That's not going to come out nicely. Negative 3 over 2 to the 35th power. And then we'll do 1 minus that. Then, on the bottom, that is 2 over 2 plus 3 over 2. That's 5 halves. So then I'm going to divide my answer that I just got here, all in my calculator. I'm not going to try to do 3 halves to the 35th power without my calculator. So right now I'm doing everything in my calculator. So we're going to multiply that by the reciprocal, so 2/5 times 2/5. And then multiply that by 8. And we end up with 4655953.9396, which is C. Granted, they could have given us a little bit nicer numbers to verify that the formula works, but that's all right. We'll deal with it. But again, I used the formula. I rewrote my information kind of in that summation notation and then used that to go to my formula and then just worked my formula down. Granted, the computations were not the nicest, but it's doable. Same idea here. Find the sum. We can see that it's, well, we'll see. So let's write the sum out. 1, negative 4/5, 4/5. So the ratio is pretty easy to get here. They're just multiplying by 4/5 each time, and it's negative. So negative 4/5 is my ratio, which means this actually goes to the 30th term, which is why I didn't fill in those indexes at the very beginning, even though they give me this 29 there, because I use that n minus 1 in the geometric sequence. I know that's actually going to be a 30. And we can see here 0, 1, 2. But now I can fill in my formula. The first term is 1, which we have. We have the sequence. So 1 minus that negative 4/5 to the 30th power over 1 minus a negative 4/5. Again, to the 30th power, I'm going to use my calculator. So, let's see. I don't think you'll be able to see it. Oh, sorry. They imaged the computer, so we don't have it like that. But so we do negative 4/5 to the 30th power. So I'm going to show you how I do it. So there's that first one. Can you see? There it is. Negative 4/5 to the 30th power. Yep. And then I do 1 minus that answer. Yep. Then I'm going to divide that by 1 minus negative 4/5. And that'll be my answer, because it's just multiplied by 1 after that. So our answer is 0.5548, but the only one that matches that is B. This one is similar to the other formula. In this case, we don't actually have to go through sequence notation. Find the sum of the first 20 terms. With the arithmetic series, I have to know the first and last term. So I really kind of need the explicit formula so I can jump to that last term. For geometric, I don't. I need to know the first term, which I do, it's 8. And I need to know the ratio, which I know is negative 1.5. And the number of terms, which they told me was 20. Again, it's just filling in that formula. They've given me 3 different information scenarios. And every single time, it's just how can I take this and find the initial term, the rate, and the number of terms. So I can just use that formula. That's why formulas are nice. And again, it's just evaluating this. Really the same steps that I did on my calculator before. So we do the negative 1.5 to the 20th power first. Don't forget your parentheses. 1 minus that answer. I know 1 minus negative 1.5 is going to be 2.5, so I'm just going to divide that by 2.5 and then multiply by 8. And we get negative 10,637.621, etc. And if we look at these, that's D. And then this one's just using it, but I'm going to show you how this setup looks. So it gives you the sigma notation. So S sub n is equal to the initial term. The initial term in this case is 0. So A sub 0, 1 minus 1.5. And then top minus bottom plus 1 would be 20. Fully set up, if we found A sub 0, that would just be 6. Yeah. And then it's just evaluating. Now, if it's another type of sequence, then we have some properties of summations that we can use to kind of break it apart, but we're not going that far. That's calculus. There is one extra level to this, though, that we need to talk about. Geometric series, because they are multiplication and division, can actually work when you have an infinite number of terms. Arithmetic can't. If you're adding something repeatedly, if you add infinity of them, you get infinity or negative infinity. But there is a special case for multiplication and division where multiplying by an infinite number of them does not give you infinity, because each successive term is smaller. And that is the infinite geometric series, the last one we're going to look at. So we'll go to the notes. So it's very simple. And it's just a simplification of the form. In fact, it's one of the easiest ones. But if you have a geometric series, so if the pattern between successive terms is multiplication or division, I didn't realize it looked like a house right there. Put a little door in a window. All right, anyway. But if it is a geometric series and the absolute value of the ratio, remember that's just the exponential base, is less than 1, then the series will converge and your formula is just the initial term divided by 1 minus the ratio. Very, very simple. If the absolute value of the ratio is not less than 1, the series just diverges to infinity, you're done. Okay. So the first thing you have to check is it geometric? If it is, and it's infinity, if you have infinitely many terms, is that ratio less than 1? and then just follow this path. So let's look back at Khan Academy for these examples. So here we have 8, 12, 18. If the following infinite geometric series converges, find its sum. So first, I need to figure out, is the absolute value of the ratio less than 1? So I need to find the ratio. The ratio is just the ratio of successive terms. In this case, 12 over 8 is equal to the 3 over 2. So that's R. Is the absolute value of 3 halves less than 1? The answer is no. It diverges. So it's not. It doesn't have a sum. It diverges. And diverges means it goes to infinity. So in this case, they're not giving me a diverge, but they do give me 8 times 10 to the 12th power, which is pretty close to infinity. Is there another answer? I want infinity. None of these answers would be right, because it does get bigger forever. Let's see. There it is. The series does not converge. It was hiding. All right. Okay. This one, though. This one will. Now, notice. The infinity up here is what tells me that this is an infinite series. The sequence formula is exponential, which means it's an infinite geometric series. So that's the things that I'm looking for to tell me. Is the absolute value of 0.25, that's my ratio, that's my exponential base, less than 1? It is. So now I'm going to use the formula. I need to find a sub I, and then 1 minus r. So the initial term here at 0.25 to the 0 power is 1 times 12 is 12. Notice that I didn't just take that first number, but I actually plugged in the 0 to verify. That is my initial term. And then my ratio is 1 minus 0.25. My ratio is 0.25. So this is 12 over 0.75. That's 12 divided by 3/4. I don't want to leave it with a decimal. I want to simplify. So that's 12 times 4/3. 12 divided by 3 is 4 times 4 is 16. So the answer that we are looking for is 16. Using that formula. We looked, it was an infinite, it's geometric, the ratio is less than 1, the absolute value of the ratio is less than 1, I used the formula. And the rest really doing the same thing, so I'll let you guys have fun with those. All right, we're almost done. I think you've only got 1, maybe 2 more assignments. Oh no, you got limits. That's algebra 2. Sorry, you got a lot more to do. But limits is pretty easy. And let me actually check what you guys have left for that. Is it just the limits? We've done recursive, that's the arithmetic sequence, and infinite geometric elements of continuity. Yeah, so just the limits, and limits are pretty easy. So all you got is 1 more unit. I will fill in those videos this week. My goal is to have all the work posted by the 15th. So all you have to do is work through that to the end. The end of school for seniors is the 21st. And the end of school for everybody else is the 29th, I believe. But we will be accepting work past that. But get it all done by then. Otherwise, I think you got about 2 more videos to look forward to from me. and probably 1 or 2 more tests on Google Classroom, and then you're done. It's for the whole year. All right, guys. Stay safe. We'll see you next time.